In the previous lecture, we have been talking about blockchain motivation and we have been talking about the underlying data structure. So we have come to the conclusion that blocks form a linked list where the nodes are cryptographically linked together, and this is called the blockchain. In this lecture, we are going to talk about the hashing algorithm. So blocks in a blockchain use hash pointers to reference the previous node in a linked list. We assign a hash to every single node because this is how we can identify them. So in this case, we can identify the first block with this hash, HJI66. We can identify the second block with the help of this hash, ZU77F. So we are going to assign a given hash to every single block in the blockchain in order to be able to identify these blocks. Okay, so basically it is very similar to fingerprints. We can identify every human with his or her fingerprints. Basically we want to do the same but with the blocks in the blockchain. So the hashes are going to be the fingerprints of the blocks within the blockchain. Bitcoin uses SHA-256 as the hashing algorithm. It was constructed by the National Security Agency or NSA. One of the most important advantages of this algorithm is that it is generic. So it is a generic cryptographic hash function. The input can be anything. The input can be a character, it can be an integer, it can be a document, it can be an image, it can be an MP4 video, for example. So input can be anything, and the output is a 256-bit long hexadecimal sequence, hence the name SHA-256. Okay, so you may pose the question that what's going to be the input when dealing with blockchains? Of course, the given block is going to be the input for the hashing algorithm. So we have been talking about the blocks in the blockchain in one of the previous lectures, and we have come to the conclusion that there are lots of data included in the block, such as the ID of the block, such as the transactions, the Merkle root, the previous hash, the nonce, the timestamp, and we are going to use these values as inputs for the hashing algorithm. So block ID, transactions, Merkle root, previous hash, nonce, and the timestamp are going to be the input for this algorithm, and the output is going to be a 256-bit long sequence. So for example, this is a SHA-256 hash, 36F47DED and so on. So it is hexadecimal, which means that it can contain integers from 0 to 9 and characters from A to F, because there are 16 characters in the hexadecimal alphabet, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, and A, B, C, D, E, and F. So these are the possible values within this hash, as you can see. Okay, so it means that there are 16 possibilities which can be represented on 4 bits, because 2 to the power of 4 is equals to 16. So every single character within the hash are represented on 4 bits. So that's why the output is going to be 64-character hexadecimal string. Basically, it is independent of the input. This is what we have been discussing. And why? Because the hash itself takes up 256 bits. This is why it is called SHA-256. And because every single character in the output is represented on 4 bits, so every character size is 4 bits, that's why the length of the output is 64. So 256 divided by 4 is equals to 64. So that's why in the SHA-256 hashing algorithm, the output is going to be a 64-character long hexadecimal string. Okay, so let's talk a bit about the features of hashing algorithms. First of all, it must be deterministic, which means that if we apply the same hash function on the exact same input, then the output must be the same. It has to be one way, which means that it is easy to generate the hash with the given hashing algorithm, but on the other hand, it is extremely hard and time-consuming to restore the original input. So it means that if we have the input, it is extremely easy and fast to generate this 64-character long hexadecimal string, but if we have this hexadecimal string, we are not able to reverse engineer the original input. Okay, so this is the second feature, and it is very similar to trapdoor functions in cryptography. Then it must be collision-free, which means that there are no collisions in SHA-256 algorithm. Okay, there are, but with extremely low probability. So basically, we can say that there are no collisions, which means that no two different inputs share the same output hash. If you are familiar with data structures and hash tables or hash maps in Java, you know that these data structures rely heavily on hash functions. And what's very important, that a hash table can be extremely slow if there are lots of collisions. So that's why the aim of hashing is to end up with a collision-free algorithm, which means that no two different inputs share the same output. And it is approximately true for SHA-256 algorithm. Okay, so we want to make these hashes unique because this is how we identify a block in the blockchain. If there are lots of collisions, it means that several blocks will share the same hash value, which means that the algorithm is not going to work fine. Okay, so that's why this collision-free feature is quite important. And then we have the last feature, which is called the avalanche effect, which means that a little change in the input results in a completely different output hash. Otherwise, a crypto analyst can make predictions about the input based on the output exclusively. So what's very important, that after we generate the SHA-256 hash based on the inputs, so based on the values within a block, we want to make sure that no one will be able to reverse engineer this hash and get the data present in the given block. Basically, this is the aim of cryptography. And this is why this avalanche effect is quite important, because it makes sure that a little change in the input results in a completely different output hash. So we are going to take a look at the concrete implementation of this hashing algorithm in the next lecture. Thanks for watching.